Welcome to week 10. You have a nutcracker assembly to do. Look in your Blackboard academic content, week 10, to download the nutcracker assembly and the parts. Make sure you unzip the parts before you open them up. You have to open up the assembly part file and finish the assembly. The instructions are in academic content week 10. Also for week 10 is I want to go over the final project report. This is found in academic content week 6. It's called MEC 100 Final Project Spring 2020. Okay, and it looks like what you see here on the screen. So you've already done your proposal. The rest of this is approximately what the grade will be, how many points you get for each thing. 100 points total for the final project report, and it is, it is 25% of your overall grade. So under the final written report, this is due Saturday, 11th week. So as it says there, number 1, submit the report in a PDF format. All pages must be PDF and merged into one PDF. So you're going to have pictures, you're going to have Word documents, you may have Excel spreadsheet for like the bill of materials. Everything must be in one PDF file, all pages merged. Title page should show your name and section number and a title of this project and a picture, an isometric pictorial of your finished product. You can do a rendering. If you want to, you can also take a picture, a photograph of it, and put it side by side on the front page with your rendering. The written documentation includes the following: description of the object, including number of parts, along with a picture of the object. I guess we already have the picture on that first part there. Group proposal, you can put that in for your page 2 or 3. Brief explanation of what the final project was to accomplish. Basically, you just answer the question, what was the objective of this final project? And then for the main body of the report, you will use the NABC format, which is explained here. The NABC format is a format we use at Kettering. It's kind of a recipe for an invention, basically. If someone says, well, I got a great idea for a new blender, okay, I'm going to use a certain different cutting edge or something. If you're creating a new item, a new product for the market, or an improved product, you basically have to think your way through from conception of the new idea all the way through to the completion of, or the manufacturing of the part. A lot of good ideas start out there from entrepreneurs, but they never get into production, or somebody else takes their idea because they don't know how to run with it. So a lot of people get stuck on the approach. They think of a good idea, or they think of something that they think is a good idea, and that approach to their product is that they say, oh, this is the greatest thing since sliced bread. But that's as far as they get. So the approach is you describe how your product is better than your competitor's product. Okay, why is it so special? Why do you think you could make something, make some money from this? And you can put the NABC, need, approach, benefit, and competition in any order you want. But approach is typically where people get stuck because they think of a good idea, but they don't know how to think it through to the end. The need. This is when you identify the need that the item fulfills in the marketplace. Not your need, not to, build up your own ego, but if other people don't want it, it's not going to go anywhere. So successful products are more than just, this cool or this fun idea or fun thing to do. They must fulfill a consumer's need. A consumer must say, in effect, I'm throwing money at you. Give me this. I want it. Benefits. Sometimes you make something better by, if you're doing a blender, you add another button. Okay, when I was a kid, blenders had like 4 buttons. There was the on and off button, then there was low, medium, high. Now you buy a blender and they're like 12 buttons. And they start off with chop, and they end up at the top end, the high speed end, at like liquefy. Because they figure people want 12 buttons. I don't know what puree means. That's less than liquefy, I think. But do I need that speed? When I use a blender, I use liquefy for everything. If I want to chop ice, I just pump the button a few times. But if you add buttons, if you add, something to it, like if you're building a new washing machine, you say, well, what people need is this doohickey. So what you need to do is you need to justify this benefit. It's going to cost more if you add, bells and whistles to a new product. Can you justify, not just say it's going to make it better, can you justify how will it make it better? Because it may make it more expensive. Add more buttons to a blender, it's going to be more expensive. Do people want that? Okay. But explain how your product will benefit or make your product better than a similar product. Remember, when you're thinking about improvements to your product, that you want to think of an improvement that will improve the product, okay, and make it better. That's how our economic engine is built. Everything, we're always improving products or making new products. It may be something you can model, this new invention, this new addition, or this new improvement. It may be just something that's aesthetics. Maybe you can change the color of it and give different color schemes. What is the new color for kitchen appliances now? What do people want now? Okay, you got to give them what they want. But benefits versus cost assessment means you assess what your product or your improvement will do to the item, make it more expensive or less expensive. If it's less expensive, well, then you can probably grab some market share. If you got just as good of a product for less money, that's good. If you're going to increase the price of your product, you better make it worth it. Here's an example. PCs versus Apples, okay, Macs. Why do people buy a more expensive computer? Well, Apple they go toward the high-end market, so they're the first one out with the thinnest computer, better resolution, not plastic but stainless steel or aluminum or tempered aluminum or an alloy for the case. They're cutting edge, and you pay for it, but they know there's a market out there for people that want cutting edge. So it costs more, but people buy it. Last one is competition. For any invention, you need to know who your competition is. That's who you're up against. So if you say, well, I'm going to make the best bubble gum in the world, it's like, well, then you're up against other gums and bubble gums. So, identify your product's competition, and try to justify how yours is going to be better than theirs. After that, it says you must make at least one improvement for your product. That improvement could be cost. You don't just say you're making it cheaper. How are you making it cheaper? Okay. Identify that, how you're making it cheaper. It might be one part you're making cheaper, it might be every part you're making cheaper, but how do you make it cheaper? So don't just say something, don't just say I'm making it cheaper, say, justify your conclusions. Manufacturability, if you can manufacture it cheaper or faster, and you know a way to do that, then explain it. The reliability of the product, if you can make a product that's more reliable for the same cost, then that's an improvement. Aesthetics or appeal, what's the favorite color people are going to want, or the different color schemes or different shapes that people would want. So think of aesthetics of it. Marketability, can you market it easier? You can even improve a product by making it ship easier. I once had a tricycle for my daughter when she was like 2 years old, and the tricycle actually folded. Under the seat was this hinge that was made just for this tricycle, and you'd pull a lever and you'd fold the tricycle up, and it made it fit into a box about 40% smaller than the tricycle when it's unfolded. So there was really no assembly required except for just to pop this thing open and turn the handlebars around and tighten them down, and it was done. The improvement on it was they did design a hinge which made that little bike cost more than the normal little bike, but they were able to fit it in a smaller box. And since it was made overseas and shipped on a shipping containers, you pay by volume, not by weight, not by number, not by quantity, but by volume. So every boxcar that they put this in, they knew that if they could make the bike smaller and that people want a tricycle that is fully assembled for Christmas morning, they're going to buy that one over one that's disassembled. So they said, there's our market, people that want a tricycle that they can open the box and pop it out and boing, and screw one little screw to tighten the handlebars, and it's done. But they saved money on the improvement. It cost them probably tens of thousands of dollars to design the hinge, but they saved over, I don't know, 1 million or 2 million units, or however they made. They saved money in shipping costs, so that's an improvement. So you have to think of a product from the beginning all the way to the end to think of improvements. Model the improvement if possible, if that's something you can model. Otherwise, you justify your cost savings or whatever. The improvement meets the need of the consumer, typically, and either giving him something more reliable or cheaper. And it's not to meet the need of the producer or the CAD operator. I do not accept the premise that I'm making this product different, I'm making it easier to CAD. No, sorry, CAD operators are just overhead. They're like the janitor in the building. They pay you to do your job, and you re-CAD it as many times as they tell you to. So we don't simplify a product, make it easier to CAD. That's not an improvement. Dimension prints. You need to create dimension prints of any non-off-the-shelf type part, a unique part. Okay, so if you had a blender, what are the off-the-shelf parts for the blender? The electric cord, the motor, and screws. About everything else, and wiring. About everything else in that blender is unique, usually plastic parts. Okay? Maybe there's some rubber grommets or something in the bottom that are also off-the-shelf parts. Anything that is not off-the-shelf that's unique, you need an NX dimension print, which means you show all views of that part, as many pages as you need, at a certain scale that you can fit all the dimensions in. So all necessary dimensions need to be on your dimension prints. Don't forget your tolerances. Don't forget your units. It's either millimeters or inches. All your parts should be in the same units. Any general or local notes, what the dimensions in the pictures don't explain, your general and local notes should explain. Don't forget to name your views. Don't forget a part name in the template border. This part name should also correspond to your bill of materials part name, so I can look between one and the other. Identify what type of material this part is made out of, each part, okay? Be as specific as you can. Sometimes when you're thinking about what parts are made out of, what kind of material, that's a way to think of an improvement on the part. But different materials have different physical properties, so you have to have the same or better properties to change the part to a different material. Don't forget a small thumbnail shaded isometric view in the corner of your sheet. Don't forget the name of the part creator, which is yourself, I guess. Normally we do this in a group, so we make sure we always have the part name. I guess you don't need the name of the creator because they're all yours. Off-the-shelf type parts, nuts, bolts, screws, things like that. These parts are readily available to purchase off the shelf. That's why they're called off-the-shelf parts. You can place one or more of these shaded isometrics, because we need basically a picture of every part you're doing, and not an orthographic view, but an isometric view. So I want a shaded isometric view of every part. That could be the picture on the corner, or it could be one sheet to put an off-the-shelf part on, or you could put several on a sheet like we did with week 3. But I do need a shaded isometric of every part, be it on the shelf or off the shelf. You need at least one assembled assembly view, like we did with the nutcracker or the hinge assembly. Okay. You need at least one exploded assembly view. Sometimes you have a part that has big parts and small parts. So if you're doing a clock, the face of the clock, the hands and stuff are basically one scale, and the gearbox in the back is another scale. All those parts are tiny. So you might have an exploded view of the face and just showing a black box where the gear is, and then you could have another exploded assembly of just the gearbox. Because if you just show the gearbox exploded on a piece of 8.5 by 11 piece of paper, the parts would be so small I probably couldn't tell them to see them anyway. So, but you need at least one assembled view and at least one exploded assembly view. The exploded assembly views are explained how to do that in the nutcracker assembly from this week. You need a bill of materials, sometimes called a BOM, or parts list. List every part in your project. You probably want to use an Excel spreadsheet for this. You need to have everything important to that part listed. Different parts have different important descriptions, but you might want a part name or a part number. description, quantity needed, the material, any physical properties that material has to have. You might list density and tensile strength or things. Any other pertinent information about that. If it's a screw, you need to identify the screw by the head, what type of head, shape of the head, and if it's a hex or torque or Phillips or whatever slot screw head. And then you identify the threads by either metric or English and what size. And those are described in appendices in the back of your textbook. If it's like an electric motor, you'd need to know the RPM at a certain voltage and things like that about just the motor and maybe the manufacturer and the model number. Wires, you'd have to know the color of them, single or multi-strand, what type of insulation is on the wire, and it's copper, so how long. So different parts have different descriptions of them. So the bill of materials is really encompassing everything. As if you were to give this report to some company, you said, here's my idea of a blender, this is all the parts I need you to make, and you're giving it to a manufacturer that's going to look at it. He needs pictures of everything that's unique so he can actually make the molds or make the models. He needs a list description of the off-the-shelf parts. So you're giving him all that information, you're cataloging it. Your dimension hand sketches can go in the back. Make sure they're PDFs. This should all be in one. This report should be in one merged PDF file, please. I don't have time to go through a whole bunch of pages in separate PDFs. If you do some extra credit, there's always, you can get a few points of extra credit. If you use a command that wasn't shown in class, so I didn't go over in class, okay? If you find something, if you know something, you need to use it. Make sure you have a separate paragraph in your write-up that says extra credit possibility here, and then detail what command it was, what part it was made on. You want to save your entire final project report, including the write-up, your isometrics, your 2D dimensions, everything that you've done in it, okay, and save it in your U drive. In this format, first name, last name, section number, call it final project, and put that in your U drive. You also need to take that PDF file and send me a copy of it, email me a copy of it. If it is larger than 25 meg, you took JPEGs of it or something, you need to shrink those things down. This thing shouldn't be more than like 10 meg of space. I don't have the fastest internet connection up here in northern Michigan, so don't send me your PDF file in a Google Drive. If attached to an email, you need to shrink it down. JPEGs are too big or something, okay? So if you have problems with that, before you send it to me, email me and ask for help or something. But email me that final written report in PDF format. Remember, all pages should be merged into one PDF file, including your hand sketches. Probably your hand sketches may be the largest electronic files, so make sure you take those pictures of those like we did with the week 1 and 2 homework, and shrink them down first before you attach them as a PDF. Written report should be emailed to me by 5 p.m. Saturday of week 11. Good luck on that. Let me know in class next couple of weeks, especially this week, if you have questions on this. Read through this. Ask your questions before class ends, please.